So we have typically within the atmosphere as air will move from areas of high pressure to low pressure. If we combine this with the Coriolis effect, we see sort of two types of airflow. We have anticyclonic airflow and we have cyclonic airflow. Anticyclonic airflow, we'll go with that one because that's on the left-hand side of the image. What we see is air flowing from sort of the center of this sort of air mass, if you want to think of it in that terms. It's an area of high pressure. Air is sinking. This is cold air, nice sunny conditions, maybe not a lot of moisture within the air, and it creates an area of high pressure. Air is always going to move from high pressure to low pressure, so it's going to move from this high pressure center to the low pressure along the edges. And as it moves, Coriolis effect is going to deflect that air towards the right. So we get this appearance of counterclockwise, of clockwise or anticyclonic flow. Everything's sort of curving in the one direction there. Cyclonic flow, on the other hand, we have once again still have air flowing from high to low pressure, but now it's flowing from the edges into that low pressure center, the low pressure eye. Once again, Coriolis effect plays a role, and that wind is going to curve towards the right as it flows into that low pressure center. Low pressure center, we see warm moisture air rising up into the atmosphere. This is going to result in counterclockwise flow. The greater the difference in pressure, the faster the air flows. So this is why we have this little two notes up there, direction and speed. Direction taken care of by Coriolis effect, where the high pressure part is, where the low pressure area is. The speed is how big that difference is between high and low pressure. And that's going to affect how fast the air flows. If we go back and look at the heat capacity of water, we can also explain why sea breezes occur and why land breezes occur. So very commonly in coastal areas, depending on the time of day, you might experience a breeze that's blowing in from the ocean, or you might experience a breeze that's blowing from the land onto the ocean. This is due once again to heat capacity. Remember that oceans have a high heat capacity. They have the ability to gain or lose large quantities of heat with only a small change in temperature. So it takes very long for water to heat up, a very long period of time for water to cool down. Land, sand in this case, has a much lower heat capacity than ocean, so it's going to heat up or cool down very quickly. In fact, in some locations in the summertime, the land surface can be 5 times warmer than that of the ocean by late afternoon. And it's usually in late afternoon where we see some of these breezes occurring, as well as the earlier parts of the morning. So what happens during the day? Well, during the day, usually in the late afternoon, we can get the creation of an offshore sea breeze. What happens, because of the fact that land has a low heat capacity, it's going to heat up much quicker than the adjacent ocean. Air above the land is going to heat up, it's going to rise, and as it rises and sort of moves up and away, cooler air from the ocean is going to flow in to replace that rising air. Why does it occur in late afternoon? Well, by this time the land has heated up quite a bit, and we have that sort of the extreme in temperature differences between the land and the ocean. The opposite happens in the evening. Then we have the creation of an offshore breeze or a land breeze. What happens is during the night, because seawater has a higher heat capacity, the air over it remains warmer, whereas over land with its lower heat capacity, it cools much quicker, and as a result, the air sitting there cools faster. Then the same thing happens. The warm air lying over top of the ocean begins to rise. The cool air that's sitting over top of the land will go flow in and replace that rising air that was sitting on top of the ocean. So you have this cool land breeze now moving outwards offshore over the ocean. So now for the rest of the lecture, we're going to take a look at storms, because storms occur in the atmosphere and are a common everyday occurrence on the ocean. The Earth and its oceans experience wide varieties of storms. So storms come in many different forms, anything from rainstorms and blizzards. These are part of something that we know of as an extratropical cyclone. We have tropical cyclones. They can also be called hurricanes or typhoons, as we'll see in a few moments. And we can have thunderstorms. So we have all sorts of different storms that are occurring every day over the ocean. Or sometimes, as we'll find out, these storms are created within the ocean or on the air above the ocean. What is a storm? Well, a storm is an atmospheric disturbance. This is going to be a fairly regional atmospheric disturbance. It sometimes, in the case of hurricanes, can cover an area of about 1,000 kilometers, but in sort of on the scale of the world, it's fairly regional. And quite often storms are characterized by strong winds. That makes sense. We know that the movement of air within the atmosphere creates winds, and often accompanied by precipitation, either snow or sleet, hail or rain. Storms are the result, and this is where the oceans become very important, but the result of interactions between the ocean and the atmosphere, especially tropical cyclones. The other thing that we have to look at when we're talking about cyclones, remember we've already talked about cyclonic flow and anticyclonic flow, is that these are huge rotating masses which have low pressure areas associated with them as well as high pressure areas associated with them. And here in this sort of silent image, we see a cyclonic mass sort of on the left-hand side there. Within the atmosphere, we can have air masses, and air masses are very similar to water masses. An air mass is a large volume of air, and within that mass of air, what we'll find is the temperature is fairly uniform, very little variation in temperature. The amount of water vapor is going to be fairly consistent in the density, and that makes sense because temperature and water vapor content plays a role in how dense the air can be. It's also going to adapt to characteristics of the surface below it. So are you moving over a polar region where things are cooler? The temperature is going to cool down within that air mass. Are we moving over a warmer tropical area where there's a lot more moisture within the air? Big thing here though is air masses will always have different densities, and this means that they'll never mix. What we're going to see is that one air mass is either going to move over or under another. And at the boundary between the two air masses, this boundary is known as a front, we get turbulence. We encounter turbulence as these two boundaries get together. And remember, there's lots of energy packed into the system, into both of these systems. Why is it called a front? Well, it almost has a warlike analogy. You can think about it as these two air masses doing battle at the point where they both meet together. Little map here. Once again, this is something I'm not going to ask you about in a test, but it shows you sort of all the different types of air masses that we can encounter. The maritime polar, continental tropical, which is hot and dry, the continental Arctic, which is very cold and dry. So there are many different air masses that exist in the Earth's atmosphere. So air masses, different densities will never mix. One will move over or underneath the other, and this results in a front. And here's a picture, illustration of a couple different air masses as well, a link to a Weather Network video on air masses. What happens with a warm front is we have a mass of warm air. Remember, warm air rises, so it's going to kind of push itself over top of a mass of cold air. And at that boundary between the two, sort of in the lower parts, sort of at that point of that sort of that wedge that's being shaped in by the cold air moving in, is we'll see a band of rain, a very wide band of rain or precipitation associated with that warm front moving in. If we have a cold front, what we see is a very steep slope. So we're sitting there in a mass of warm air, a cold front or cold air is moving in. What we see is a very steep slope. It's almost like that sort of half circle, or that quarter of a circle we see there. And that band of restriction, or that band of precipitation, is much, much smaller, maybe only up to 150 kilometers in width. Let's take a closer look now at two of these types of storms. Let's look at extratropical cyclones, and then let's look at tropical cyclones. And both have air masses involved in their formation. So extratropical cyclones, the big thing to remember about an extratropical cyclone is that it forms between two air masses. In order to have an extratropical cyclone, you have to have two air masses in that front occurring between these two air masses. They're a low pressure system associated with both cold, warm, and occluded fronts. So you have a cold front or warm front coming together. And where we typically see these extratropical cyclones, it's not always the case, but the majority of the time, is they occur at the mid-latitudes at somewhere between 30 to 60 degrees. What type of activity can we associate with these extratropical cyclones? Well, you get cloudy skies, definitely not sunny out there if you have these. We see rain, we get thunderstorms, a lot of instability and turbulence within the atmosphere, a lot of energy moving through these systems, blizzards, nor'easters that we see here in Nova Scotia. Extratropical cyclones move counterclockwise in the northern hemisphere. This is counter to sort of what we expect as the Coriolis effect. The Coriolis effect, we expect everything to be diverted to the right. But if you look back a couple of slides where we talked about cyclonic and anticyclonic flow, it should explain why we see this counterclockwise movement. And quite often with these extratropical cyclones, if we view them from space, we see this really characteristic comma shape to them. In Atlantic Canada, we refer to these extratropical cyclones as nor'easters. And here we see in the satellite image on the bottom right, you can just kind of see the tip of Nova Scotia at the very upper right-hand corner of the image. But once again, you see that really comma shape associated with extratropical cyclones. And once again, here in Atlantic Canada, it can be associated with anything from huge rainstorms to blizzards. In contrast, we have tropical cyclones. So remember, extratropical and tropical cyclones are two different things. Tropical cyclones are also known as hurricanes in the North Atlantic and Eastern Pacific, and typhoons in the Western Pacific. So it depends on where you are in the world what you call this particular type of storm. It's a mass of warm, humid, rotating air. We see that this tropical cyclone, its birth is in warm tropical parts of the ocean. And what happens here is it doesn't occur between two air masses, but it occurs only within one air mass. And here we have a lovely picture of a tropical cyclone, Hurricane Gonzalo, just up off the coast of the Turks and Caicos in October 2014. Once again, we see this counterclockwise flow. So tropical cyclones are born within tropical oceans. You need warm air, you need humid air. There's a lot of energy within that system, so you need a lot of energy to feed into that system. Warm waters, more energy to feed that storm. And as I said, they form inside one warm humid air mass, usually at locations between 10 and 25 degrees, either north or south. So we have these typical breeding grounds, as we see in this map here, where we see these tropical cyclones forming. In order to be classified a tropical cyclone, you must have sustained winds of at least 119 kilometers an hour or greater. The air temperature is really important too. These things don't do well in cold air. Remember, we can have extratropical cyclones with snow and blizzard-like conditions associated with them. Tropical cyclones, we need an air temperature of about 26 degrees. It needs that warm, humid air as a source of energy to keep it going. These storms can be very wide, up to 1,000 kilometers. The storm itself can extend up to 15 kilometers in height, and the eye, which is sort of that low pressure system or center in the middle of the storm, can sometimes be 15 kilometers wide. So there's a certain recipe that's required to create these hurricanes, these tropical cyclones. You need, first of all, a pre-existing weather disturbance. So often you start off as sort of this little small tropical storm that can grow into a hurricane. You need warm water, and that warm water actually has to extend to a depth of about 50 meters. So it just can't be that the surface layer is warm, but you need a significant chunk of warm water to help power the storm. We see thunderstorms associated with this. The thunderstorms do a great job of transferring heat from the ocean into sort of fuel energy for the hurricane, and mix it all together, and you might get a hurricane. Even if you have all these conditions, you might not get a hurricane, but if everything is just perfect and the conditions are right, a hurricane will be created. So just a little rehash of the previous slide. What we see here is we start off with a thunderstorm. We have warm surface air rise. You remember, warm, moist air rises because it's less dense. This can turn into a tropical depression, which then can turn into a tropical storm as long as you're continuing to feed warm, moist air into it. And this eventually can form a hurricane. And we'll talk a little bit more about the specifics of the formation in the next slide. If you do want to learn more about hurricanes, I strongly suggest watching this National Geographic video. Once again, as I've said all along, we'll say in the future, if you have problems with this link, definitely get in touch with me and I will send you a new link. So how do we actually create this rotating mass of warm, humid air? What happens is that warm, moist air or humid air is moving across the ocean, and as it should, it's going to start to rise into the atmosphere. As that warm, moist air rises into the atmosphere, it's going to start to cool. This is all things that we've talked about before. It's going to condense, and it's going to start to condense and form rain, precipitation. What happens is, as that occurs, as that rain forms, as that condensation occurs, heat is released into the atmosphere. It makes the air lighter, and that air now is going to rise up further. What happens then, though, is moisture from the ocean is going to move in and take the place of that sort of cooler condensed air rising. And what happens is it's going to start to set up that circulation, that rotation that we see within a hurricane. So hurricanes are like an engine. We need to continue to give it fuel for it to go, continue to move. You lose the fuel, the hurricane is going to start to die out. The other thing that happens is as that warm air rises up into sort of that middle part where the storm is going to form, we have an area of low pressure underneath, and this is going to cause, remember, air moves from an area of high pressure to low pressure. This is going to cause even more air to rush in, which then rises and cools. More clouds are formed, more thunderstorms occur, more precipitation occurs. And eventually you're going to release enough heat energy to create this hurricane and continue to feed this hurricane. Just another slide that you can take a look at on your own time and work through how these hurricanes form. A little bit more detail than what I've talked about in the previous slides, but definitely take a look at it. And if you have any questions, contact me. Why do tropical cyclones rotate? Why do extratropical cyclones rotate? But we'll talk about more about tropical here. If we notice one thing, we notice that they rotate in opposite directions in the southern hemisphere. Tropical cyclones rotate counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. And we've talked about this already when we talked about anticyclonic and cyclonic flow. It has to do with how air moves from an area of low pressure air moves from areas of high pressure into low pressure, and how that air is deflected by the Coriolis effect. Once again, we have that low pressure eye, so air is going to move from the high pressure zone to the low pressure, and as it does, the Coriolis effect is going to pull that air and it's going to veer off to the right, and the overall net effect is it's going to appear as though the cyclone is rotating to the left counterclockwise, even though the Coriolis effect is pulling everything to the right. Remember, it's a case of how you're looking at what your frame of reference is. What happens in a tropical cyclone? Well, storms are named. Every year, a list of storm names are released. It goes through the alphabet from A all the way to Z. And then if you get past Z, we start at A over again. Sometimes, depending on the severity of the storm, certain names will be retired. During a storm, winds get faster. They can get faster than 118, 119 kilometers an hour, get very strong, powerful winds that can do a lot of damage. We have powerful rain bands, so, heavy precipitation. Waves are whipped up because of the huge amounts of wind that are blowing through the system. There's lots of energy being packed there. And the other aspect is that at some point, remember we have that low pressure eye, is that the storm is going to pass over you. You enter the eye, you get sort of a period of calm, and then you get the tail end of the storm, and once again, hurricane, cyclone, typhoon-like conditions. Another characteristic of tropical cyclones is a storm surge, and a storm surge can actually tend to be more destructive than the cyclone itself. So the storm surge occurs as a big bulge of water that's very quickly, very rapidly pushed onto shore. You can see a change of water levels of a few meters in just a few minutes. So the storm surge actually moves ahead and with the storm. It's a wind-driven water and can do, as I said, tremendous amounts of damage. The water levels along coastlines can easily reach a height of 10 meters. It's very difficult to move in a cubic yard of seawater. If we look at a cubic yard or a cubic meter, typically you can weigh almost a ton. So you can just imagine of what the damage can do, this type of storm surge can do. It can push cars, it can push boats out of the way, it can even push houses out of its way. This is just an image of a storm surge coming ashore off the eastern coast of the United States. So once again, it might appear wave-like, but it's this bulge of water that's just going to sort of keep coming. With it, once again, because it acts almost like a bulldozer, it can move and transport huge amounts of debris with it that then compound the problem or compound the damage that can be done by the storm surge. To give you a sense of just how high water is being pushed on shore by the storm surge can be, this is from a hurricane that hit the southern United States, especially the area around the Gulf of Mexico, New Orleans a number of years ago, Hurricane Katrina. And you can see in the image on the left how far up the bark on the tree has been stripped. This is a height of 7.65 meters, and this has been attributed to the storm surge as the water comes pushing past that and basically essentially stripping all the bark off of the trees. So you can imagine this wall of water coming ashore that is almost 8 meters in height. How do storm surges form? Well, there's a couple of things that go on here. So as this hurricane is moving towards land, it creates this bulge of water sort of on the land side. It piles the water up on the land side and it creates a storm surge. So we have this wind-driven surge. We also have a part of the surge that's created by pressure. Remember, we have an area of low pressure. We have areas of high pressure. It's going to create this sort of this pressure-driven surge. So what happens, the actions of the winds will pile up water. Typically is up to about 80, contributes up to 85% of the surge. Waves will push that water inland faster than it can drain off. This is something that we call wave setup. And that represents about 5 to 10% of the surge. So we have this wind-driven bulge as well as waves pushing that water on land. And then the low pressure of the hurricane will suck water higher into the air near the eye. And this accounts for about 5 to 10% of the water that moves on land during the surge. So it's a combination of three factors as a bulge of water is created as that storm moves onto land that creates the surge. We're going to finish off this lecture talking a little bit about Superstorm Sandy. And this is a hurricane that hit in October 2012. And it hit the eastern coast of the United States and extended all the way up towards places like New York City and even up into Nova Scotia. Why was it called Superstorm Sandy and not Hurricane Sandy? Well, it was a combination of both a tropical storm and an extratropical storm. So a hurricane, a tropical cyclone, and a nor'easter. I know I just call them storms, but a nor'easter, an extratropical cyclone. They actually converged together to make this huge mega storm. There have been other destructive storms in history. Hurricane Katrina is one that springs to mind. But this storm did a huge amounts of damage to the eastern seaboard of the United States and parts of Canada. So Hurricane Sandy only reached a Category 3 storm. That has to do with the fact of how fast the wind speeds were going. You can actually have categories above that. It covered an area of almost 2,000 kilometers and was one of the costliest hurricanes in U.S. history, one of the largest Atlantic hurricanes on record. And not only did it have a combination of that tropical storm as well as an extratropical storm, but we also saw that it coincided with periods of really high tides that were associated with a full moon. So not only do we have this huge intense storm that led to a rise in sea levels due to the storm surge, but we also had high tides, higher than normal water levels. So we had three things going on here. We had that extratropical storm, that low pressure area over eastern Canada. We had the tropical storm, Hurricane Sandy. We had high tides. And this really played a role, especially in New York and New Jersey, on really basically unleashing fury along the coastline. So Hurricane Sandy, here's a map showing its path. Once again, it was bred down in sort of the tropical parts of the Atlantic Ocean. It made its way up along the eastern seaboard and finally sort of came on land or made land just around New York City and New Jersey. One of the things that happens is when a hurricane starts to travel through land, that fuel that starts to, really add energy to that system, it starts to lose that fuel very quickly and they tend to die out. Finally, by November 2nd, it made its way sort of to northern New Brunswick, where it started to really lose steam. Associated with Superstorm Sandy or Hurricane Sandy was, as I said, a storm surge, and quite an extensive storm surge. And the effects of the storm surge are amplified by the fact that we had higher than normal water levels due to a high tide. It was a full moon. And this just gives you an example. This is in New Jersey of some of the damage that was caused, not so much by the hurricane winds, but by the storm surge. So extensive coastal flooding. You can see that there with the pickup truck in the upper left, coastal communities there on barrier islands on the far right. This pier here that had an amusement park on it, completely decimated. As you can see, there's a before and after shot. That whole corner that had the roller coaster on was basically washed away and left behind as this tangled mess within the ocean. Once again, not so much the wind played a role in this and creating all this damage, but it was the storm surge that caused a lot of this damage. Some before and after shots taken along a barrier island off the coast of New Jersey, once again showing the devastation caused by Hurricane Sandy, by this associated storm surge. So up above you see pictures taken in May of 2009. Really nice beach houses. Down below you can see that a lot of these houses have been completely destroyed. Some places the beach has completely disappeared. The arrows on here point to the locations of certain houses, certain features, and just to sort of let you know where they showed up or ended up after the storm. It wasn't only New Jersey that was hit, but downtown New York was hit as well, New York City. Here are some pictures from downtown New York City. Because of the storm surge, experienced coastal flooding. You can see some of the tunnels that go to other parts of the state completely flooded, the subway flooding. This is on October 31st, I think it's on Halloween, October 29th that this occurred. Extensive power outages, fires followed that just leveled entire blocks followed after this, not so much in New York City, but in New Jersey. So the devastation was far wide-ranging and quite costly. So that's the end of Module 5 in atmospheric circulation. Hopefully now you know a little bit about how air travels in the atmosphere and how tropical and extratropical cyclones are created. Any questions, definitely feel free to contact me. Thanks.